Hi, welcome back. So we're going to basically start mm, slightly a newer topic in this called electric dipoles. Before we get into the dipoles, I think we will actually complete a few portions of electric fields itself. What is a field? Okay, so we have kind of understood till now what is a charge. We have understood very clearly, and we have also understood to a good extent what is an electric field. So we said that electric field basically is something which is nothing but the force per unit charge. Like if you keep one test charge in the vicinity of another charge, it will experience a force, and how much force it experiences divided by the number of amount of charge is what basically is the field. So we have always seen that field as nothing but a force per unit charge. Now, when we are actually writing a definition of electric field, we wrote electric field is simply equal to K into Q, or 1 by 4 pi epsilon naught, that is what is the K, into Q divided by R square. So that means it is just that it has everything like the force, Coulomb's law, but only one Q, that is the Q which is causing the electric field, source Q. Okay, and this is, if you want to have this basically as a vector, then this R as a vector you have to put as the what we call a unit vector to show the direction. So ultimately, this is actually a vector which has both magnitude and direction. We have to be able to show that as a vector. And suppose if I keep one charge here, let's say I have a charge here of some plus q. I have a charge, and if I actually calculate at this point, assume that I want to calculate at this point, what is the electric field? So how do I do that? I just basically take a small test charge and keep it here and see how much force it experiences divided by the charge itself. So that means you will finally get a vector which is basically a magnitude and direction, and its direction will be away from this because it is, if you, this is positive, and if you keep here also positive, so this is basically nothing but the vector that you can write at this point. At this point, you can write that vector. So now, even if you actually go and find out the vector of all these points, let us say I am going to find out on this imaginary circle, I will take various points at this point. For example, if I want to calculate, now you can very clearly see that this distance and this distance are same. R is same, so its magnitude becomes same. Only its direction in this case will be here, this like this. Okay, and if you keep it, let us say here, it will be like this. All these have exactly the same magnitude, and if you keep it, let us say here, it will be like this. And you can even keep it wherever. I mean, you keep it here, 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 here. All these places you can keep it a test charge, and you find out the electric field, and you plot it as a vector. Okay. So this is another vector you can see of the same size though. So this is the vector here. So we can actually write like this at any point, all the vectors basically. So what is common about all these vectors is that they are all of the same size, but they are all different directions. So now what if I actually calculate, for example, okay, on another imaginary circle which is basically slightly bigger. Here I will calculate. Now that would have the same direction as this, however it would have a smaller magnitude. So it would be basically slightly less magnitude. And you can see that these are all having lesser magnitude. than the other one. So you can calculate for this also. Everywhere you can see that it is slightly lesser magnitude, mainly because owing to the distance. So square of the distance you can see it varies as the inversely as the square of the distance, inverse square law. So they are all smaller. These lines are all smaller, and you can clearly say that if I am going to draw even one more line as an imaginary circle around this is basically because the for a unit charge the uh, the electric field is spherically symmetrical. So it's very important to understand what is the spherical symmetry. Though I have written here, if you see here, I have written as just a circle. But when you keep a charge here, it is not just that the charge produces field here, it produces field in the front of the board also, and it produces field in the back of the board also. So it's all the whole sphere it is not just a circle. Though I have shown a cross section of the sphere, it's actually a sphere. So this whole thing what I am showing out is, imagine something like a sphere with a lot of sharp arrows on all directions coming out. Okay, that is what I am showing you here. So though it looks like a circle. So here if you see in the next level it is even smaller, smaller than the earlier. Why it is smaller? Because it is further, like this. Since it is at this point when I calculate using that formula or using the test charge, and it is small. Now this is how you represent the electric field. So the electric field around a point charge is represented like this. However, Michael Faraday was the one who actually started trying to put this as a field around the charge, and he came with this idea that this has some difficulties writing like this, because you see now I have written carefully chosen points which are quite farther apart. Suppose if I wanted to calculate the charge here and then charge here, okay, then I have to put one arrow here and another arrow I have to put on the top of this, like this. Okay, and that gives rise to a lot of confusion in drawing. The lengths of the arrows will not be known. You have to use many different kinds of colors and all that. So he came with a more simple idea. Okay, that's very interesting. See what idea he came with. He came with an idea called electric field lines. He actually called them as electric lines of force because he realized that they are force. But later, the word got changed to electric field lines. So what are those electric field lines? How do they look like? So he just decided that I'm not going to draw several such small vectors. Instead, I'm going to simply draw a line which actually goes through this like this. The whole point, single line, full line. And you can put on the line, you can put the as many arrows as you want. Okay, this is all simply a line, a single line, no breaks in the lines. So at any point you go on the line, I mean this line I have written here basically certain number of lines, but you can write as many as you want. Okay, as many as you want you can write, and everywhere you can calculate. Just have a higher resolution if you put more lines. So he says that you can write these lines like this and calls them as electric lines of force, or now we call it electric field lines. So these electric field lines, if you see carefully, watch it here, there is one flaw in this whole approach. Looks like there is one flaw. What is the flaw? Can you tell me? In the earlier one, we used to have these vectors which tells us both magnitude and direction. Now suddenly it shows only you go here, it shows the direction. Where is the magnitude? So it looks apparently that we have lost the information on magnitude. But Faraday was clever. So he says that instead of doing, he says that you have not lost the information. So you know what you have to do is Wherever there is a higher density of these lines, there the magnitude is higher. And wherever there is a lower density of these lines, there the magnitude is lower. What do you mean? So you can take for example, you take this part. Okay, I am writing this circle here because this is basically a sphere. In the sphere, I am going to cut it here, in a small area. I'll take. Okay, in that area, you see there are so many lines are passing through that. Whereas the same sized area here, I will write same sized area. You can see that lesser number of lines are passing through that. So you may ask basically saying that it depends on how many lines you are drawing. Yes, of course. But what you have to understand is the lines you are drawing, you can choose as many number of lines as you want to draw. But the same lines go through this and go through here also. Same lines. Hence, relatively if you look at it, basically, this one has lesser number of lines than this. So, if you actually calculate at any given, when you start drawing, actually, if you go and write lots of lines like this, when you do, okay, lots and lots of lines, and you want to basically take one small area, okay, in that small area, number of lines you take divided by basically the surface area of that small area, you will get basically the density. So the density of these lines tells us that basically the electric field strength or the field value of electric field is higher than suppose here. Same lines we extend here, the number of lines that pass through is very less. So the direction is given by the arrows, and the electric field strength, or what we call the magnitude of E, is given by the density of these lines. So that is Michael Faraday's idea. So however, uh, is it right? It's all 100% right. Is there any other doubt in your mind if you think about it? Okay. Now, what we want, we have figured out. One is that we said that the direction it is giving us the magnitude in terms of relatively you can calculate with respect to some constant factor, you know the magnitude. Okay. So, here it is more, here it is less, here it is more, here it is less, we know. But you may ask a question, okay, it is more fine, but is it really as much more as it is supposed to be given by this formula? It is as much more as it is given by this formula. That means this formula tells us that if you go by a certain distance, okay, then that distance, if you substitute square of that, that would give you the, in the sense that if you go double the distance, E will become 1/4. If you go 3 times the distance, E will become 1/9. Is it happening like that here? Is a question. So for which you can actually derive and show that it happens. Okay, I'm going to basically show you how it really happens. Okay, in a quick small derivation. Okay. So in a circle, if you take, for example, in a circle, the whole area, whatever we have, okay, the area of a circle, not area, I'm sorry, the circumference of a circle, if you see, from here to here, if you want to calculate what is the distance, how do we do it? Total area, if for total distance basically is pi d or 2 pi r. If this is r, 2 pi r. Okay, so 2 pi r is for 360 degrees, or we can say 2 pi radians. So to go this much distance, let us say this is distance L you want to go. For L, for L. Now we want to find out basically if this is theta. Okay. For theta radians, how much is the distance? See what I am asking, simple ratio proportion. If I go around for 2 pi radians, I will have covered 2 pi r distance, that is circumference. If I go theta distance, how much I have covered? That is the question. Now that is very simple. Okay. So you can say basically for 2 pi it is 2 pi r. For theta how much? That is the question that we are asking, which is nothing but r theta. 2 pi gets cancelled. Okay. So we can say L is equal to r theta. Is the formula that you got. So you see, I am going to basically use this formula in a different way. Okay, I am going to basically talk about, instead of a circle, okay, I have a sphere. So you will have to imagine that this is a sphere, okay, not a circle. So if I actually take on the sphere surface one small area, okay, I am going to take one small area, circular area, and this area I am going to basically connect it to the center through a kind of a cone. Cone's base is slightly curved, you can see it's a cone. What we did here is we took actually a curved line and connected it to the center. So here we take a curved surface and connect it to the center. And what you see here in this cone is that angle. Now this angle is not a theta, it is a solid angle. So plane angle is just two lines. Solid angle is like this. It is the peak of the tip of the cone, whatever angle that it's formed is called a solid angle. And solid angle we generally don't try use theta. We use like this ohm kind of a thing. Okay, omega we call it. It's called capital omega. Okay. So we use this for solid angle. This is this. And let us say this is basically some surface. Let us say delta S is the surface. This surface area is delta S. Now you see the like a circle contains 2 pi radians of angle. Okay, circle contains 2 pi radians. Similarly, the sphere contains an angle of 4 pi radians. Steradians. That is the unit of a solid angle. The 4 pi steradians it contains total, okay, inside. So for 4 pi steradians, you have basically the whole surface area, which is nothing but 4 pi r square. 4 pi r square is the surface area of a sphere. Okay, now the question basically is small delta S. So this side is delta S. If it is delta S, what is the angle? Angle is omega. Okay, what is the value of this delta S? Okay, what is the value of this delta S? So this length is r again. So we are doing exactly similar kind of thing, not very different. Okay, I have just written the angle this side and surface area this side, just inverted. Now this is basically nothing but our delta S. So delta S has to be equal to what? Let us see. Okay, now for 4 pi steradians, you got 4 pi r square area. For omega, how much? That is delta S. So if 4 pi get cancelled, so delta S is nothing but omega r square. Do you see this? The surface area is equal to delta S, omega r square. Here it was L is equal to r theta. Here delta S is equal to, or S is equal to omega r square. That is the difference. So this comes in solid geometry. Now this delta S is nothing but now omega r square. So for a given omega, if you see basically, the number of lines that actually come because of our electric field lines for a given omega, it is same. Okay, that's not going to be changed. So if you keep a charge in the middle of this, there are so many different field lines which come through this. Okay, for this omega, if you go here, wherever you go, number of field lines is actually same. Okay, so if you want to calculate the total number of field lines per the distance, okay, if you see per surface area, so density of field lines is equal to, okay, you can see that the number of lines that go through here, yes, which I will call that as basically number of lines as n, okay, divided by the surface area delta s, okay, so which is nothing but n divided by omega r square. So I said that number of field lines per given omega, okay, that is constant. So this whole thing is actually a constant. So constant by r square. You see, actually, the density of field lines is nothing but constant by r square. And you see what is E? E is, if you don't change the Q, okay, Q keeping constant, 4 pi epsilon naught is constant, it is something constant by r square. So even E is some constant by r square, and the density of field lines is also some constant by r square. So that tells us that it is okay to represent density of field lines, okay, as the field strength, and that is basically the cleverness of Michael Faraday. Okay. So now let's just move on to understanding the field length, electric field better. Now we will move on to what is called as another concept. So the electric field lines, I also want to basically tell you that if you want to keep, for example, okay, a single charge, that what I talked about, the electric field length we saw how it looks like. So this is a positive charge plus Q, and field length looks like basically this is how basically the field lines look like. Okay, this is for a charge which is positive charge. That means always field lines go from the positive charge towards basically infinity here. Okay. Now if you take for example negative charge minus Q. Okay. Even in minus Q, if you see, it is all basically similar kind, except that it is all coming inside. Because if you keep a charge here, positive charge, it gets attracted to minus Q, and hence the direction is inward. And this direction, this looks similar except the direction is different. Now in this case, you can see very clearly that it is from infinity to that point. Okay. Now, if you now talk about what about if I keep two charges? Let us say I am going to put one positive charge here, one more positive charge here. So how does it look like? Two positive charges, if I am going to keep together like that, how do they look like? Okay. So it looks like basically, I am going to put it like this. It looks like so you have to practice basically drawing this. If you are asked to basically draw, how does it look like when you actually put two positive charges together, okay, nearby? So it looks like this. It's they're just basically they're going to repel, and you can very clearly see here in the middle here, there are no field lines. That means the charge basically the field here will be zero. Why is it zero? We can see here if you put a unit positive charge, that will be pushed by this guy and pushed by this guy and equally pushed in the opposite directions, and net force is 0. So net forces means 0 means net E also is 0. So if you had actually negative charges in both of them, they also look like this, only the arrow reversal will be there. So what if you have a positive charge and a negative charge? Positive and negative. How do they look like? So then actually they look like this. You can see that for all these, for the negative charges here, this side is negative and this side is positive. For the negative charges, all the arrows are coming towards the negative charge, and for the positive charges, all the arrows are going away from the positive charge. So practice writing like this. What about writing the 3 charges? Can you draw? So such things you can practice. So now basically you can very clearly see that field lines, how do the field lines behave if you ask a question? Okay. So one statement that you can say is they always go from positive to negative charges, or positive to infinity, correct, or from infinity to negative. So this is how the field lines actually do. And second important thing is we have to understand here, if you look at a field line and if you ask a question in this field line, by looking at the field line, and I am taking, let us say, one point here, let us say point P. At point P, what is the field strength? What is the value of electric field? So value of electric field means it is its magnitude, and also what is its direction, if you ask that question. Density of the field you can calculate here, and that is nothing but our magnitude. You can always calculate within the formula also. And if you draw a small tangent here, if you draw a tangent at that point to the curve, that gives, basically, that curve actually is giving you the direction of the magnitude of the electric field. So by drawing, because since it is a curve, you can draw actually a tangent, okay, and find out what is its direction. Now, it is imperative from this, another second important point, which is electric field lines never cross each other. Electric field lines never actually cross each other. Suppose, assume that an electric field line crossing each other like this. Okay. So what does that mean? It means that if you want to find out the electric fields at this point, okay, we have been told that it is possible to find out electric field. Okay, its magnitude is fine actually, suppose, but its field strength, its direction, you see, this curve has this direction and this curve has this direction. Now it has 2 directions, so it cannot have 2 directions, it can only have 1 direction, like that. So that means it cannot cross each other. So that is the second important rule. What are the properties of electric field lines? If you ask properties, you will be asked. There are such questions which come. Properties of electric field line. If you go, so what are the properties? First property is they always go from positive to negative, and second property is are from positive to infinity. Okay, second property is electric field lines never cross each other. They don't cross each other. Okay, and the third one, you see, is that they never form loops. They never form loops. So that means that you cannot have an electric field line which is in a loop like this. Why is it so? Because they always originate from a charge and end up in another charge. Okay, and the other important point is that they are actually, if you see, okay, I will actually have to say one more important point here. Electric field lines never cross each other. Okay, in the sense that in the place where there is no charge, in the place where there is charge, they may cross. Okay, so because at the point of the charge, it is the amount of field, how much it is not defined, because it becomes almost an infinity, because the R is 0. So that's the exception. And here they never form loops actually means that because they are force field, okay, the force is in this direction. So for the force to be conservative, electric field lines are supposed to be conservative force, in the sense that, okay, it is actually, if it increases in one direction and decreases, it has to decrease in the other direction. It cannot keep on increasing and come back to the same thing. In the sense that it is like saying, if you write like this, it is like saying that you climb down the steps, keep climbing down, climbing down, climbing down the steps, and finally you reach the same place where you started from. That cannot happen. If that can happen, then electric field lines can form loops, because they are force fields. So the conservative force, it's the electric field is a conservative force. Conservative force. So because of that, they never cross each other. Whereas magnetic field, because of that, they never form loops. Magnetic field lines form loops because magnetic field lines do not represent the forces. Okay, these represent actually the forces. Okay, so that is basically our understanding of electric field lines. So moving forward, so now we will look at the next important concept, which we call electric flux. Third one, electric flux. So what is electric flux? You must have heard about the flux of water, a liquid flux. What is meant by liquid flux? Flux of water, let us say. There's a huge flux of water which came in, which means basically nothing but what we are saying is, let us say if you have a certain area, okay, let's take pipe or a stream of water is coming, and assume that in this area some water is just coming out. Okay, so if the water is coming out through this, now if you take for example the surface area, that is the delta S, cross section of the area, and if you also find out how much of water is coming out in given amount of time, okay, so that is nothing but the velocity of water, velocity of water. So water flux or liquid flux is given by nothing but velocity into delta S. Velocity into delta S. Now the question basically we have to ask is, this delta S, what we are talking about, is basically kind of perpendicular to the flow of liquid. Assume that it is perpendicular to the flow of liquid, like this. So then we can say delta S into V. V is in this direction. This is the direction of V. So instead of that, actually, if you had cut it like this, okay, in this V is in this direction, you have cut it like this. Even then, the amount of liquid that comes out for in a given amount of time is same. It's not going to increase. So that means basically, if you multiply this delta S, this area of cut into V, it will be a big value. I don't want that value. I want to know exactly how much comes out. So in a given amount of time. So the V into delta S, we have to also look at what is the angle of that. So instead of perpendicular, it is making some other angle. Okay. So to this, so that angle, and I said this angle in this case basically this angle. Okay. Or this angle is this is the v direction, and this is basically the real perpendicular to the surface. The surface is this. I have taken a perpendicular to the surface, and this is the direction of v. Okay, this I will call the perpendicular to the surface as n. Okay, so that n is in this direction, v is in this direction. Now, really, what we need to do actually is we have to look at this theta and say it is nothing but v into delta s into cos theta. Because if you do cos theta of this, okay, you will actually get the real direction. Okay, cos theta of this, you see. What is the cos theta? So it will align with the v if you do theta. Cos theta is nothing but adjacent divided by hypotenuse. So adjacent is equal to hypotenuse into cos theta. So that means you want to get this in the same direction as v. So that is why we are going to write it here as v into delta s into cos theta. Now, so for fundamentally what I am trying to say is that this delta s making an angle, and I want to only get this much, this delta s, and not this angled one. So to get that, I need to use the cos theta. So this can also be written as v into v dot n delta s. So this is the flux. This is the n, v dot n, v dot n. So now that's the dot product that we have learned in the last year. So the same thing is actually applicable for what we call electric fields also. Okay, in electric fields, what happens is the if you talk about basically in electric field, there is nothing that is flowing, but there is electric field like this E. Not flowing, but it's a conceptual. And if I take certain area, let's say delta S, within that how many electric field lines are going? Okay, that we know. And if it is a perpendicular direction, then we can take as easy E into delta S. So electric flux, we say, is nothing but E into delta S. But however, if it is at some angle, then we will say, okay, so I will call this electric flux, small flux area as delta phi is equal to, I read it as phi. So electric flux, I read it as, I use it a symbol called phi. Okay, and delta phi, because whatever is going through delta S, I call it as delta phi, which is equal to E into E dot n into delta S. So I am just doing the same thing as velocity, okay, that getting the cos theta into picture. Now you see the way basically we understand this electric flux is, suppose if you have a, let us say, some closed area, closed volume. This is my closed volume. Okay, need not be spherical, some other shape, closed volume. In this closed volume, if you take a certain small area, let us say this is a small area that I am going to take, small area. So in this small area, I will call this area as delta S, and the this delta S, okay, there will be from inside, let us say there is some charge is kept inside, and there is a lot of electric field lines which come through this outside. Now these field lines, that is what we call E. Okay. E into delta S. Okay, the delta S, if it is aligned differently, we use basically n. N is this perpendicular to this. Now n actually is perpendicular to this, and basically a kind of a vector, unit vector perpendicular to delta S and showing outwards. Okay, in the case of a closed surfaces, we can easily denote it outside. So what we call as n to be positive if it is outside. Okay. Now the whole of the surface area, okay, surface area, when we talk about a small area segment, we always talk about the area segment as a what we call a vector. Okay, area is considered as a vector. You see, is a vector. So that's for why, that is only for our convenience sake. Okay, so area, this delta S is a vector. So and we can simply say instead of E dot like this, if you consider area itself as a vector, we can say E dot delta S like this. So what is delta S? Delta S is actually nothing but this area. However, it is represented by a line in the direction of a perpendicular n, okay, and having the magnitude numerically equivalent to the area. If the area is, let us say, small area of 0.1 meter square, then for 0.1 you write a picture of an arrow of 0.1 meter length and put one arrow on the top of it, that is represented as a area vector. Area is now represented as a vector, which means line having a magnitude and a direction. So that is outward vectors. So if that is the case, now say this is just not related to only flux. Okay, this concept of area being denoted as a vector is going to be there all the time now onwards. Okay, so please remember that. So delta phi is nothing but E dot delta S. Now I want to find out the whole flux that is coming out of this everywhere. It's going everywhere now out of this. So what do? We say that basically we cut this into small areas. Okay, so many different areas, and we will say E phi is simply equal to sigma of E dot delta S. So many such delta S's you take and take a sigma of all of them. That is the total number. You are counting all the E's. So E dot delta S you will get. And this is actually approximate. Huh? Why is it approximate? Because delta S, however small you are going to cut basically, along inside the delta S itself, the area, the E may not be constant all the time. Okay, E may be varying within this much small area, in which case we have made a mistake by multiplying. So, but if you make the delta S actually tending to 0, then this is going to work. So, if delta S tends to 0, then it becomes an integral. Okay. So, we will simply write it as phi exactly equal to integral of E dot ds. This is the important rule that we have to remember. Whenever we actually have to find out the flux, then if you integrate the E field around this area, the surface integration when you do, you get phi, total flux. So this is basically the, so we will not get too much into this area. Okay, we will, if you understand this concept of what a flux is, that is sufficient. So it's going to be using it in the next few sections. Okay, so now this is basically, we have covered electric charge, electric field and electric flux. Now we are going to move on to another very important point, concept, which is a very new concept for you. You have probably not encountered that concept before. So what is that concept? So we are going to talk about the next concept called electric dipole. This has not been addressed till now. So what is an electric dipole? We have actually seen this dipole, okay, but not in the concept of electricity. But in magnetism, we see that we have a bar magnet, okay, which we call north and south. So this is one pole, this is another pole. So there are two poles which are stuck to each other, means there is a constraint in terms of how they are arranged. That means this pole cannot go away on its own. This pole cannot go away on its. They are connected together, okay, through some entity. Okay, such a thing is basically a dipole. A dipole is nothing but two poles. So why is it useful? We'll see that. Okay. So now the thing is that in nature, a lot of such dipoles are available, okay, like permanent magnet. Okay, and not just that, even in electricity, there are dipoles that are available. That means where are they available? I will talk to you at the end of it. But what is the electric dipole? Similar to this, you have one charge here, okay, another charge here. So this is, let us say, plus q, and this is minus q. They are separated by certain distance. Now this distance, what they are separated by, they are very nearby. So it's like a normal magnet. They are very nearby. Okay. However, they are basically in contact with each other in some other way. So they don't. We can't separate. So that such a thing is called as an electric dipole. Okay. Now this electric dipole, if you ask electric dipole how much of total charge is there, total charge is actually 0. So if total charge is 0, why? Because plus q minus q added together, you can add charges, it is 0. So total charge is 0. So does that mean the total electric field around it is 0? Just because charge is 0, is electric field 0? Think about it. So what we have to understand here is, suppose if we had, okay, the charge, one small, I am just writing a point charge in a big way. So this is one charge plus q. Just on the top of that, if you had put actually a negative charge exactly at the same point, if you had put a negative charge minus q, okay, plus q and minus q on top of each other, in the sense that not on the top, oh, it's like in the same position, if we can put, okay, it's not possible in the same place, in the space you can't put two things together at the same time. So let's say if you had put it, then the total charge is 0 and total field around it also is 0, because any point in this you take, let's say you take this point P, the distance to this point from plus q and minus q is same. So one produces basically a field in this direction, another produces a field in this direction, they cancel out, 0. But you think about a scenario like this, it is not. So you have a point here, let us say P. Okay. But this point, this minus q produces a field like this, and plus q produces a field like this. Okay. Now the real field is nothing but basically added together vectorially. This is the real field E at this point P. It's not 0, because this point P is at different distances from these two. The length of this and length of this will be different. Their directions are different. You have to vectorially add them to get it. So hence, electric field around a dipole is not a 0. It has certain value. Now the only thing you have to understand is that the more farther you go away from a dipole, somewhere here if you go and want to calculate basically what is the field, you suddenly realize that the distance from there and distance from there to here, both of them are almost similar, just very far. Okay, so this, let's say the distance between these two dipoles is some d, and this distance is r. So if r is very greater than d, okay, then one of them is pushing, another one is pulling, they almost cancel each other and it becomes almost 0. Okay. So if you go very far from the dipole, the electric field strength is quickly diminishing to 0. But if we are nearby, it is not. Okay. However, it definitely is not as much as that of a single charge. So other charge slightly neutralizes. But how much it is, how to calculate that. So that is what we are going to do and get some kind of a understanding of a dipole. Okay. So now what we will do is, first of all, okay, we will define a dipole like this. So you have plus q, and you have, I'm just for the sake of clarity, I'm going to write down here slightly big, longer length between them. Okay. Minus q here. Now we're going to basically find out if I have to actually put uh, one line here. Okay, that is called along the axis of a dipole. This is called along the axis of a dipole. Okay. Now, if I put certain basically a charge here, let us say at point P, some other charge, or if I actually want to find out the electric field at that point, you can easily find out. Okay. And the other possibility is if I will put actually a kind of what we call an equatorial plane. What is the meaning of that? That means that I have a plane, okay, cutting plane on this. So every point on that plane actually is equidistant from plus q and minus q. So there, if I see what is the electric field, how to calculate that we will see. Okay. So two things we will do. We will do on the axis of the dipole. We will put we will find a point electric field at certain point, and on the equatorial plane of a dipole, we'll put some point and find out what is the electric field strength and its direction. We could put somewhere else arbitrarily, okay, some point P and find out what is that, what is the electric field there. But that is mathematically harder to do. So that is outside the scope of your level. Hence, we will only do simple things that are possible on the line, along the line, and that will give us an idea, okay, along the equatorial plane. And one more important thing that we need to understand here is that let us actually write down some. We need to have a certain kind of a definition of the directions. Okay, so I am going to draw an arrow from plus q to minus q like this. Okay, and this arrow, whatever it is showing, that direction I will basically call the direction of basically P, something called P. Okay, and I am going to define P as dipole moment. So we are going to do that in the next session in a little more detail. Okay. So why I am talking about this now itself is that this word dipole moment is extremely new word. Like how dipole is a new word, dipole moment is a new word. And when we are introducing the dipole moment, immediately we will start using the dipole moment everywhere. Okay, and you will be in a shock because you don't understand it. Okay, it's like force. It's been taught to you from the 5th standard. What is a force? Now, when you come to 11th standard, you have been already told a billion times about the force. So, when I use the word force, you understand it. Whereas, when you talk about dipole moment, I'm going to keep on using it a lot from tomorrow or from the next session. But you have only heard it once, so it's harder. So, now you are expected to basically pick up very fast the concepts. Okay. So, don't give up this as I don't want to know this concept. Without dipole moment, you cannot survive. So, in all, everywhere in physics, especially electricity, magnetism, everywhere dipole moment is going to be there. Okay. So, this is not actually a momentum. It's called dipole moment. Okay. It's like a moment of a force, that kind of a moment. So, what is this dipole moment? So, we are going to define dipole moment as nothing but, see what I am going to show is P is defined as, okay, Q into D. Magnitude. It means that there are two charges here, Q plus Q and minus Q. We will take one of them and we will take the distance between them, D. If you multiply these two, because they are important, how much charge, how far they are. Those two important information when you multiply, you get actually a dipole moment. Okay, and this dipole moment I will also give a direction. The direction of the dipole moment basically is direction from negative to positive. That is the dipole moment direction. Okay, this dipole direction that what we are giving from negative to positive is something very specific to physics. Okay, so it's in all physics and mathematics where we use all these things, we will use it. But in chemistry, when they talk about dipole, they will give a different direction to it. Okay, so don't get confused with that. So here we understand always that the dipole moment is nothing but how does the dipole form? Dipole is whenever there are two charges equal and opposite, they are separated by a small distance. D is the dipole. Okay, you got it. Now once you got that, that dipole has a feature, a character. Okay, what does it? What is its characteristic? Its characteristic is it has some charge and is separated by some distance. We multiply those two, and we call it as dipole moment, one number. And that number is basically going to tell us its features, its character. Okay. And direction is from negative to positive. So with these two things, basically, I will end this session saying that we have got an introduction into the dipole. We know what is a dipole. We know what is a dipole moment. Now we are going to see in the next session, by keeping my test charge around the dipole, I will have to find out what is the electric field there. How do I compute it? So it's very easy to compute because you can compute with respect to this, calculate it, add it up vectorially and you get it. So which we are going to do. And those are two derivations which you are likely to get even in the exams. So let's do it in the next session. Thank you.